Hey folks, so I'm just going to make this quick video for my friend Stefan in Germany. We talked about making an arc gap, and he suggested I put a commutator on here, and I do have some commutators I could do something like that in the future. But first, what I'll do is this is about a third of the way. I guess it's a third of the way between this coil and here. There's 3 coils, so this will be a third of the way. I'd like it to be really in the center of the coil, but this will be like 1/3. So, but it's gonna have, that's gonna create an imbalance, hopefully, that will get some interesting effects. And it's just a loose connection. We should get some sparking on there if we can even get it to crank. I don't know how well that connection's holding, but I might have to make a little better connection there to hold together. These wires are so thin you can't even really see where the wire goes in, and it's probably about a mile of wire on there. There's quite a lot of wire on there. And my cat monkey girl's here chilling out, so I'm gonna go ahead and plug this in and then give this a kickstart. It's a Joe Newman coil on there. Well, it's the Joe Newman effect. It's a Tesla coil, but I call it the Newman effect because, well, we talked about that in other videos. I'm gonna go ahead and plug this in. Let's see, unplug that, and okay, it's plugged in. Oh wow, getting some arcing already. So let me crank it up. Whoops. Uh-oh. Oh, it won't. Okay, let's see. It won't crank because of the loose connection, but I already had arcing across there. That was kind of neat. So let me just set this down. I'm gonna go ahead and make a little bit tighter connection so I can go ahead and crank it. Let's see. Hopefully I'll be able to crank it. Okay, so I'll just try to crank it, and then I'll just pull that connection loose, maybe with my pencil, so I don't get shocked. That could be some really high voltage on there, and this is plugged into 120 volts AC. This is the only circuit I got over here that I got household current. Okay, so it's plugged in. It's 120 volts. And you see it's not overheating or burning up because of the Newman effect. Now it's cranked and running. See, it's drawing virtually no power at all. So that's your free energy secret, or over unity or whatever, for Stefan Hartmann. That's my buddy. So let's look at this. Let's see, try to create a spark gap maybe. Whoa. Dang, it was going. Yeah, well, that was interesting. Alright, let's see. Maybe I can just get enough of a connection that I can crank it, re-crank the motor here. Let's see. Because it's still plugged in to 120 volts. Okay, there we go. It's so hard to crank. I need to put it like a hand crank on there. Come on. There it goes. Yeah. Ah. Get this out from under it. Well, that was interesting. It was running, but keeping the motor going with the arc gap was the problem. Okay. Nope. Ah, pulled the connection loose. There it goes. Yeah. And we still got an arc gap. Okay, let's try to widen this arc gap without killing the motor. That's the trick. Focus my lens. Ah, it killed the motor. I don't have enough torque now. What it needs is a flywheel maybe to help keep some momentum, because this is really an ultralight rotor and it's running at fairly high speed. Killed the motor. Careful how I do that spark gap. Okay, let's try this again. Focus my lens. I killed it right away, but if it would stay running, I think I could get some really good arcs. I'm having trouble getting it to crank now. Well, let's see. Alright, well, I'm going to unplug it and just go ahead and tighten the connection. This is really a lot of work. Now we're running, but I got a really tight connection on there, so it's been hard to create a gap. I'll bet you I could take a loop from there, I can ground it towards something else that's not even connected, or ground. I bet you would arc really good, like to this metal over here, or even over here, or even all the way over to there. Let's see, try that and just well, I guess it's okay to leave this running since it doesn't get hot. No cooling fan, but it doesn't get hot at all. You saw it just sitting there with the rotor locked in place, and it didn't burn up because there's such a high resistance on that coil of wire, that Tesla coil. But see, all the magnetic field goes through instantly. That's what Joe Newman was trying to tell people. So look, yeah, there's a lag in the current, so there's really no current going through there, but all the power of the magnetic field goes through. So mechanically, it's doing all the work, and you know, has good high torque. But all that power is really coming from the magnets, because there's just zero current going through there. There's tiny little wires, and they're just not even getting hot at 120 volts. So that's there's just no doubt that that's what it is. And that's what he tried to tell people. Like, look, this is free power. It's coming from the magnets. It's magnet power, you know. But really, it's atomic power, or it's probably, you know, something to do with the Casimir force, basically with the quantum forces of time, the nature of time. It's the same thing causes hysteresis, in my opinion. It's the same things that cause like inertia. It's just a tendency of an object to stay. It's probabilities. Well, it's really, you have to just use quantum mechanics, because time is the factor that's not there. And you know, like, how could something behave like a particle or a wave at the same time, and this or that? You know, it's not free energy totally. It's obviously it's coming out of somewhere, but it's probably nuclear force in the magnets itself. It's somehow the nuclear force is converting over, and it's getting a little bit, you're transmutating just a little bit of that magnetic material, is getting slightly weaker. There's such a tiny amount you could never measure that with anything, or even if it's just flat out 0 point energy coming from the quantum vacuum. If this is quantum vacuum energy and that's all it is, it's still going to be, it's not going to, you could suck as much of it as you want, it's always going to just fill back in and reach equilibrium. That's the thing about it. It's the forces created by the vacuum pressure itself. Now, we have actually pretty high atmospheric pressure here. So like, electrons don't flow as easily when the pressure is high. You know, explain that. It's easier to store static charge on a really dry day. That's why you get shocked when you live up north where it's high pressure day, it's real dry. That's another thing too with the water. Water, that's The water vapor is basically like the grounding conductor that's pulling the electricity out of the air. So you don't really, when you're wet, you don't really build up a static charge. You can't hold on to your electrons because they're getting stripped away by which really we call the hole, or the p-type material. It would be like the female. It's like a wanting, or it's the hole, or it's the lacking. I think it's called like the yin maybe versus the yang. I might have that backwards, the male and the female. But you know, even in plumbing we have male and female. But in electricity, yeah, water is like a positive charge, and we consider the electrons or the telluric currents, or you know, the earth batteries, the electrons. You know, it's kind of skeptical on particles, what particles actually are supposed to be. It's all just information. It's better to treat it like they do, is just say it's quantum information, just for purposes of computation. Because since you can't really see it anyways, you know, it's a wave, it's a particle, it's subatomic. You're never going to be able to physically see this with your eyeball. So any philosophy you come up with, as long as the math works and the machine works, you know, hey, the devil's in the details. But if the math works out and the computer can solve it, and then you're sitting there figuring out, oh well, now that I understand how it works, see, then we can apply it, we can visualize it, and we can actually simulate it. You know, someone could get on there and simulate and say, oh, this is what he was talking about. Now we can do this and we can do that. But first you have to understand what's happening, why it's doing that, what those alignments are, and then be able to calculate to do what you need to do. But Joe Newman, you know, may he rest in peace. He tried to show these things to everybody, and so this motor's now it's starting to kind of run a little bit warm. I'm gonna go ahead and get a wire and try to jump across there. Let me see. And hope I don't get shocked or nothing. Hey, that's working pretty good. Let's see. I can smell ozone, definitely. I can feel the hair on the back of my hand standing up. Maybe I shouldn't be holding this wire like that. Doesn't seem to be affecting the motor much at all. Oh, well, that time it killed it. Alright. Well, okay, Stephen, so that's a good idea then. I'll go ahead and make a commutator to get a really good. That's a pretty high speed on there too, so I'll just put a commutator on the rotor to make an interrupter for that, and I might just put like different taps at different places. You know, we'll just get very, very Frankenstein, very Tesla. You know, we'll kind of give it that 1930s Hollywood movie thing going with the lightning. Welcome to my laboratory. Alright guys, so yeah, that's gonna be fun. I'll make a spark gap on there. It was very interesting that it didn't even really seem, once the motor's up and going and it's in synchronous phase, you know, like, first of all, there's just can't really be any sufficient current going through there before it reverses direction at 60 cycles. And of course, I know at the time and the way it's set up, it should be running at 1800 RPM. So if I put, let's say we just double that, or put 3 or 4, I mean, one of mine, I might have a commutator that with like 12 segments or something would be really neat, you know. So that would actually be like 1800 RPMs times 12 breaks. So you know, like what, 116,000? Is that right? It'd be like 160 kilocycles, or no, 116 kilocycles. I don't know. I'm not going to even try to do the math in my head, but yeah. All right. Well, that's all for this video. Hope you guys enjoyed it. Thanks for watching.